postdoc, but he's still doing at the Royal Observatory of Belgium, where he's working in the team of Tim van Oost and Veronique de Haan, also on the topic of rotational fluid dynamics with both geophysics as astrophysical intake. And so that's also what his talk of today will be. And so I'll give you the floor, and afterwards.
Okay, thank you, Joris. Well, thank you all for coming, and well, especially to Joris for offering me the possibility to come and talk to you a little bit about what I've been doing after I left the IvS. And well, I want to talk in general. I'm not going to give a lot of specific details about anything in reality. I just want to give you more like a general view of rotational fluid dynamics and why that is important, both in the planetary science context, but as well in the astrophysical context. So let's see if this works. Yeah. So since it's April's Fool's Day, I'm going to start first with it's kind of a prank, but I don't know if any of you have ever visited Quito in Ecuador, which is at the equator. So if you go to Quito, in the capital of Ecuador, there is like in the outskirts of the city, there is a monument where they have drawn the line of the equator. So this they call it the middle of the world monument, la mitad del mundo is in Spanish. So latitude 0 degrees, and they have a little, well, you know, some monument, and there is this basin. It's a basin like this big, where there is water, and there is a plug at the bottom where you can unplug, you know, take the plug out and let the water drain. And so this is how it looks like. So that's the basin, and there is a person that, you know, attracts the tourists. It's not an official. Well, I hope it's not an official person. But the person just calls people around and say, well, okay, so you're now in the middle of the world. We are at the equator. And since we are exactly at the equator, there should be no Coriolis forces. So the person proceeds, takes the plug out, and as the person drains the water, puts a little bit of you know, some leaves to visualize the flow. So sure that once the water has been sitting there for a while, you pull the plug, and really nothing really happens to the leaves. They don't really appear to spin in any direction in particular. So then the person takes the bucket under and moves the whole thing to one side of the equator, right? Pulls the water again, well, it's plugged again, and then we say, now we are north of the equator. I'm going to unplug the thing, unplugs it, puts the leaves, and you see the leaves going in one direction. Then goes to the other side of the equator, does exactly the same thing, and then you see the water spinning in the other direction. But it's fake, because well, there are two reasons actually why this doesn't work just like that. Because there is a number called the Crosby number that measures the relative importance from inertial forces to the Coriolis force. So in an object that is so small like this basin, the inertial forces are really strong. Like actually the velocity of the flow is much larger compared to the velocity of the rotation of the Earth. So the inertial forces and the Coriolis forces, that ratio is much larger in that basin, and that is why you have this Crosby number much larger than 1 But if you consider a hurricane, which is a very large system, right? The velocities involved are actually comparable to the rotation of the Earth. So the Crosby number there is very small. And that is why hurricanes, or in general cyclones, have a preferential direction if you are in the north or in the southern hemisphere. So that's one of the reasons why these experiments are just fake. Yet there is another reason why this wouldn't work. Even if you say, let's assume that the Crosby number is actually very small in the experiment, but it still wouldn't work. And why is this so? Is because the spin axis of the Earth is not really constant in space. So if you were able to mark the location of the North Pole or the South Pole, actually, because there is nothing really solid at the North Pole or at the South Pole, if you could mark it, you will see that the South Pole actually moves, and it's actually wandering about, and it can be displaced up to up to 20 meters, and a few months later it goes back, and it kind of makes some sort of a pattern that you can see in the plot, in this plot here. And you can see this is in meters, and this is also in meters. So if you think of the equator as the line that is 90 degrees, or the plane that is 90 degrees to that line, then of course the equator is going to move, right? So the actual location of the equator is moving. So the Coriolis force being in one direction or in the other wouldn't really work, because it depends on where exactly the line of the equator would be. So that's yet another reason why the experiment wouldn't work. Okay, so there is this picture also that shows the location of the tropics. This is in a highway, I think in Chile, where they have marked the location of the tropic along the years. So you see these things are actually moving. Okay, and so how do we know the location of the pole with so much precision? Well, actually, it's quite interesting, because we do that by using radio telescopes. And there are many radio telescopes situated in many places in the world, and they form a network, and they can observe if there is an object, very distant object, like a quasar. You can observe that object with 2 or more telescopes, and you can measure the time delay between the signal of the quasar. The quasar is really, really far away, so that's one of the reasons we use them. So we can, with the help of a very good synchronization clock, then we can know the exact time delay between the 2 radio telescopes. And if you do that for many radio telescopes, and if you actually look at many quasars around the sky, you can establish what is called the celestial reference frame. And then we can know exactly, well, with a very good precision, how the axis of the Earth is moving. That's how we know how to make the plot that I showed you earlier. Okay, and there is this very nice visualization. I don't know if okay. That is showing you the axis, the instantaneous axis of the Earth as it goes around. This is the precession of the Earth, is the long, circular motion of the Earth. But then superimposed to that, there is these tiny variations that are called nutations. And those nutations are the ones that are causing the motion of the pole in the plots that I showed you earlier. Okay. And so it turns out that we don't know exactly where that signal from the nutations is coming from. A good part of it is actually from the loading from the atmosphere and the oceans that causes variations in the water cycle, and other factors make the axis move a little bit. But even if you take into account those factors, and if you take into account mantle deformation, atmospheric and ocean loading, you can still see a residual that is still present in the nutation signal. And well, some people say that that is probably coming from the core of the Earth. And well, it's something that we have been trying to figure out exactly if this is actually telling us anything about the structure of the Earth inside. So it works like this. So we know how the forces that act on the Earth, the gravitational forces from the sun and the moon, and to a lesser extent, the other planets. But we know them quite accurately. And we also know how the Earth is moving quite accurately with the technique that I just mentioned. And so this is kind of like it's like an inversion problem, because the input, sorry, you know the input, the output, then you have to figure out what's in the box, what's in the black box. It's actually very much like this. I don't know if you have seen, well, all of you have cooked eggs, right? And you know how to tell one from the other, for uncooked and cooked eggs, right? Everybody knows? So you put it to spin. The one that spins nice is the one that is cooked, right? If the one that is not cooked, it doesn't spin nicely. So that's essentially what we are trying to do, because when you spin it, you're applying torques to the egg, right? And then you see the outcome. Does it spin in a nice way or not? And then you can infer, oh, so the interior of the egg is fluid or it is solid. So because it's all about the moment of inertia of the egg. So if you have a fluid egg, then the only moment of inertia that you are acting on when you torque it is the shell. But if you have the full cooked egg, then is the full moment of inertia of a solid egg. So of course it's going to spin differently. So this is what we are trying to do. Then trying to figure out if that signal from nutations is actually telling us anything about the interior of the Earth. So there is something in the underside of the mantle that is kind of like inverted mountains and valleys. There is some sort of topography in the interface between the fluid core and the mantle. And we don't know exactly how that looks like. We don't know if it's if it's very rough or if it's very smooth. We actually have no good idea. But the notations are probably telling us something about the rugosity of this topography. But also it could probably is telling us also about the conductivity of the lowermost part of the mantle, because if you have some conductivity there is possibility that electrical currents can flow next to the core, and you can also have then magnetic torques acting on the Earth. And moreover, there is, well, some people say that there is a stably stratified layer at the top of the core that is stratified in density, and that layer would, in some sense, would kind of buffer the motion of the core itself from actually coupling properly with the mantle. So these are, for example, 3 things that we would like to know that the nutation signal is probably telling us. So I've been working on that problem. It's not an easy problem, and well, it's something that we are going to, well, hopefully something will come out of that in the near future. Okay, but now I'm going to tell you a little bit more about the motion in the fluid. So, well, we already know that the Earth is precessing. It's kind of like this, although this is missing the rotation of the Earth. But we all know that the Earth is precessing at a 26,000 year period. And so that motion is caused, of course, by the torques of the moon and the sun, but mostly by the moon. And well, it's what determines the seasons. And to give you an idea of what happens to the fluid in the liquid core of the Earth when there is such a motion of precession, I'm going to introduce an experiment just to show you, give you a more specific idea of how the fluid will respond. So this is something that I worked on when I was a PhD student at Maryland, like Joris mentioned. And at that time, we built an experiment to study the geodynamo, just to see if we could get a magnetic field out of the flow of a liquid metal. But the first experiments we did were with water. So this is basically a 3-meter sphere ball. It's a sphere that is filled with water. So the total weight is about 20 tons. And the inner core, this has the same size or relative size as the Earth's core, like the inner core of the Earth. So, but the very first experiment, once we finished building the whole thing, the very first experiment was we fixed the inner sphere to the outer, because they can spin independently, but we fixed the inner sphere to the outer, so that they would rotate at the same time. And then we put it to spin very fast. And it's actually, sorry, I was kind of loud. But it spins super fast. I don't know how to, well, I'm not gonna go back because it's gonna start screaming again. But the idea is super basic. So you have a ball full of water and then you put it to spin to constant rotation rate for a long time. So we did some calculations. So we expected that at the beginning, the water was, of course, at rest, and the container was spinning. And we expected that the water will spin with the container at like a solid body within half an hour. But we waited up to 8 hours, and we never saw that the water was actually quiet, like at rest with respect to the moving sphere. So we have this signal here that is you see the cursor here? Yes. So this signal is from some transducer that measures the wall shear stress at the surface of the sphere. And at the beginning, you see a lot of noise because it's just the turbulence of the water, but then it kind of calms down, but it never really goes to zero, as you can see in this zoomed-in region. There was always an oscillation, and no matter how long we waited, there was always this oscillation. So we thought that we had done something wrong, so we actually spent more than 2 weeks trying to find out if there was something wrong with the experiment, but no, it was actually working fine. So it really took a while before it dawned to us that the experiment is not in an inertial frame, because the spin is moving with the Earth. So as you can see here, the experiment has some orientation with respect to the axis of the Earth. And that orientation is the cause of the discrepancy of this remnant fluid motion. And it works like this. So the water tries to spin up with the container, but say within an hour, you have the axis of the container has already moved 15 degrees, which is what you move in 1 hour. So the water tries to keep up, but never really catches the actual direction of the experiment. So if you look at the experiment, you'll see it spinning for a long time. But if you imagine that you make the the surface of the experiment invisible, then you will see that the water is crooked. Is also spinning, but the axis of the water is crooked, which is very weird. But that's, and the angle at which the difference between the rotation axis of the experiment and the rotation axis of the water, that angle is determined by how much precession you have. And exactly the same thing happens to the Earth, because the Earth, as I mentioned before, is precessing. Now, that motion, I have to do this little dance here before I explain this slide. Maybe I should go back and say, imagine that I am in the experiment, and I am like embedded in the water, and so I extend my arms, right? And the rotation axis of the experiment is my body, and I'm going to leave my arms freely move with the water. So what happens is that then you do something like this. Oh, wait. I don't know if you follow. So here, I am in this orientation. The water is in this axis, right? But I am spinning in this axis, and my arms are moving like this, right? So from the point of view of the rotating experiment, I see that the water goes like that. So it spins in one direction, and then in the other, with an axis that is in the equator, in the equatorial plane, as seen in the rotating frame. So that is the flow that is happening. That flow has a name. It's called the spin-over mode, and it happens to be the most fundamental inertial mode of a fluid. There are more inertial modes. That was the one that I just mentioned, is kind of like the fundamental one, but there are other ones that have different frequencies and they have different flow patterns. And they are all caused by the Coriolis force in the fluid. So you probably know also about the jet stream that is actually causing this weather these days. So the jet stream has some undulations, right, that go all around the globe in the north, and also there is another one at the South Pole. And the undulations are actually Crosby waves because, well, these are caused by the Coriolis force. So these are, technically, the Crosby waves are also inertial modes, or inertial waves. When that Crosby wave has too much amplitude and kind of detaches is when we have sometimes like very cold regions that are coming from the pole and come to lower latitudes, and we get the weather that we get now. What is also interesting is that if you have a memory of the recent heat waves, like for example the heat wave, it was not really a heat wave because it wasn't that cold, but there was this time of very good weather like 2 weeks ago, right? So that is actually caused by a stationary pattern in the Crosby wave that is supposed to be in the jet stream. That Crosby pattern is supposed to be moving all the time, but sometimes, because of the difference in temperature between the pole and the equator is not so strong anymore because of global warming, we get more possibilities that pattern kind of gets stuck in a geographical region, and that is what causes either like a region that has very good weather, or could be worse, could be just a heat wave, or the other regions having too much rain. But normally, if there was no global warming, then that pattern should shift smoothly. But, well, it's kind of a problem now. So in a more mathematical way to explain the inertial waves is that, well, you can explain them as an oscillation that is restored by the Coriolis force. And the way to see it is you start with the Navier-Stokes equation that controls the dynamics of a fluid. And you have this number here, the Crosby number that we found earlier. And if that number is very, very small, remember, that has to be very small. And there is another number here that is called the Ekman number. This just measures the viscosity of the flow. And this is the Coriolis force. So if you start with that equation and you drop this term because you're going to assume that the Crosby number is very small, you end up with this equation. And that equation can be solved with this ansatz. It's just a plane wave. And if you look at the resulting dispersion relation, you see that the dispersion relation has a dependence that is the frequency of the wave depends only on the relative direction between the rotation axis and the direction of the wave. So if this is the rotation axis and this is the direction of the wave, then this angle is completely determined by the frequency of the wave. Another very weird thing about these inertial waves, these plane inertial waves at least, is that the direction of the flow of the energy, meaning the group velocity of the wave, is in this direction, while the phase velocity is completely perpendicular. That is one thing that probably has in common with internal gravity waves. But that thing is, these two facts are really like special and characteristic of the inertial waves. Now, if you have a plane inertial wave, it has to reflect when it finds the surface, but the reflection law is not like the Snell's law, because it has to have, has to keep the same relative frequency, the same relative orientation with the rotation axis. So it always makes equal angles, but with the normal of the surface. With the spin direction instead of the normal of the surface. And you see that it can form patterns just like this. But you can also have global modes instead of just normal modes, normal waves. You can have also what is called global modes of the inertial modes. And this one in particular is the spin-over mode that I just showed you. And it has, you see the typical streamlines. But these are other ones that have different frequencies. They have different azimuthal M numbers. They have different latitudinal structure. And this is actually, this figure is computed by a colleague of mine, Jeremy Requier, that he's working also on these modes. Now, okay, so we talked about inertial waves and inertial modes and what they are, and how do they relate to the Earth, like to the motion of the Earth? Now, the Earth as a solid object has 4 rotational eigenmodes that are not related to the fluid. Well, almost, that's not quite exactly true. But there is something that is called the Chandra Wobble. The Chandra Wobble is something that you get always when an object is spinning and the spinning axis is not, doesn't coincide with one of the principal moments of inertia of the fluid, of the object. So it will try to wobble in space. So if the Earth is oblate, it has a figure axis, and that figure axis doesn't always correspond to the rotation spin axis. So that causes the wobble of the Earth. That's called the Chandra Wobble. It has a specific frequency. It's an eigenmode. There is another one that is called the free coordination that in reality is the same as the spin-over mode, because it's basically that the mantle is rotating at some angle, right? It's actually oscillating, but the fluid core, which is called the fluid outer core here, is this blue, is also kind of oscillating, but at a different angle. And they keep the relation, but they are always moving like that. So this is yet another eigenmode of the Earth. And now there is the free inner core notation, which is basically the same thing, but for the inner core. And as the inner core, it can have a different orientation, and it can also have its own wobble. But apparently, the inner core wobble hasn't been really observed, while these other three have been completely observed and very well characterized. But I call the attention to this one, because this one is essentially the same as the spin-over mode that I mentioned. So you sometimes hear claims that inertial modes have not been observed in the core of the Earth. Well, that's technically not true, because the most important inertial mode, the spin-over mode, is identical in this case to the free core notation, and that is an inertial mode. So, okay, so how can these eigenmodes, the four rotational eigenmodes, can be related to the eigenmodes that I showed you earlier about the fluid, the inertial modes? Well, this is the work that I've been trying to do for the last probably 5 years. And it's actually quite simple. We started first without, imagine a planet that doesn't have an inner core, just has a liquid, completely hollow and liquid core, and it has some sort of flattening because it's spinning, and this is the figure axis of the mantle, and this is the spin direction, and there is a little bit of flattening, and I'm going to consider that the flow in the fluid in the core has some viscosity. Therefore, I can write that as an Ekman number, which is basically the ratio of viscous to Coriolis forces, the flattening, and the moment of inertia. Well, this quantity is actually like the inverse moment of inertia of the mantle. So these are the three control parameters of this system. So for the Earth's mantle, this value Q is small. For Mercury, because Mercury has a very big fluid core, the mantle of Mercury is kind of thin, so it's much larger. And for example, Enceladus, which has a very, very thin icy crust, if you compute the equivalent parameter Q, it has a much larger value of 1.6. So what I did was to compute the eigenmodes of the flow together with the eigenmode, the rotational eigenmodes, and see how they interacted. So this is what I got. This is a figure that is showing you the full spectrum of the eigenmodes that go from a frequency. This frequency is actually compared to the rotation rate of the planet. So this is actually omega divided by the rotation rate to make it dimensionless. And the inertial modes always have to go from -2 to 2. And you see all these points. Each point represents an eigenmode. And what I'm plotting here is the ratio of the kinetic energy of the fluid compared to the kinetic energy of the mantle. So if you have, sorry, the other way around, the mantle to the fluid. So if the mantle doesn't move much compared to the fluid, then you have a very small number. And these are basically the normal inertial modes that you will get if the mantle was spinning with uniform rotation. It was not like it was kind of forced to spin in a uniform rotation. But there are some very interesting modes, especially this one. This one happens to be the Chandra Wobble, which is recovered after the model, And this one is called the free coordination. This is again the one that I explained to you. And there are these other ones that are very close to the FCN. So this is more or less a diurnal frequency, as seen in the rotating frame. So these are two of the rotational eigenmodes of the planet, but together with the rest of the inertial modes. But bear in mind that this is not simply a superposition of the inertial modes and the rotational modes, but rather they are actually coupled in a very strange way. So this is one of the weirdest things that we haven't really understood properly. This is the parameter Q. Well, I'm changing basically the moment of inertia of the mantle. And this is the frequency of some eigenmodes. This in blue is the frequency of the free coordination or the spin-over mode. And it has some specific frequency, but as you start changing the mantle moment of inertia, the frequency changes until it reaches some point where it starts making this very weird dance with the other modes. And, well, this is what happens to the frequency. And if you plot the same, but with the damping decay factor of the mode, you know, as an eigenmode, you have an eigenvalue, and the eigenvalue represents the frequency. The real part is the damping decay, and the imaginary part is the frequency. So this is basically plotting the real part of the eigenvalue versus the imaginary part of the eigenvalue. And so this means that the free coordination being so, you know, the first one here is the least damped mode of the system. And as you start changing the moment of inertia, the damping starts, well, increasing in magnitude until it reaches some point where it starts doing this very weird thing. This is more or less at the same place where this interaction takes place. So what is happening? This is some sort of a avoided crossing that I'm showing you here. Probably this is more clear. This is again the damping and the frequency, and the color is the value of Q. So you see that for some specific values of this of the parameter of the system, you have this very weird path that the modes make. So this, for example, this one corresponds to these modes at the top that do not interact, right? Because they basically are independent of Q, so they don't change. And this one is basically following this and this and this and this and this. So they follow a very, very specific pattern. So basically, this is an avoided crossing. Look, maybe you have seen this in, well, I don't know if you ever had a class in quantum mechanics, but in quantum mechanics it's usually explained that you cannot have you can have a crossing between two quantum levels. But that also happens, it's not just from quantum mechanics, but it also happens in a system of two masses with a spring. Anything that has two eigenmodes, two different distinct oscillation modes, can have avoided crossings. The interesting part here is that the avoided crossing is not just because the eigenvalue is complex, because we are considering the damping of the modes. It's not just that you avoid in frequency, because you can have an avoided crossing in the frequency. For example, here, well, you see that the FCN mode is going and it crosses the frequency with no problems with other modes. It has the exact same frequency, for example, here, with another inertial mode, but it's no problem, because the damping is very different, as is represented in the color. The color simply represents the damping. And so you can have a crossing in frequency as long as the damping of the two modes is very different. But if the frequency and the damping become too close, then there is a problem. The modes cannot cross. They have to avoid each other either in the real part of the plane or the imaginary part of the plane. So, yeah. So that's what's happening. We tried to see if there was any evidence of this in the core of the Earth, but it turns out to be extremely difficult because the extreme values of the parameters for the Earth, especially the Eigen number, which is the viscous to the Coriolis force ratio, the Eigen number is very small, but it's essential because the viscosity is what provides the damping. And so we couldn't really see if something like that is actually happening in the Earth, but at least we noticed it. And we know that it could happen for example, in another planet that has, well, it all depends on the value of Q. And, well, I actually don't know why I put this slide here. Well, this slide is probably a little bit unrelated to the frequency crossings, but it's probably, I think I was planning to shift to another topic here, and it's about, well, okay, so it's kind of like the same topic. It's the damping of the free core nutation. So we did a study of how much is the free core notation damped according to our numerical model. And it turns out that there is a measurement from the real Earth that we can compare to. Because, you know, if you have a forcing system, like the torques, the lunisolar torques on the Earth, and you can measure the response of the Earth, and if there is a phase delay between the forcing and the response, that delay is related to the damping. So you can actually estimate the free core nutation damping from observations from the radio telescopes. You can estimate what that damping is. And we did the comparison to study the damping from our numerical method, and we were thinking that maybe because of these very weird things that happen in the core that I showed you, like this inertial waves, like rays, and you can see these rays also here. They're a little bit, well, they're kind of spread over. So that means that there is a lot of shear in these locations. But the most important shear is actually at the boundary. But we wanted to see if the shear in the bulk was anything important that could be maybe taken into account, but it turns out that no, that the most of the damping actually comes from the friction of the flow at the boundary. So that's the most important part. Okay, and this is yet another work in progress. So we developed this code to study the inertial modes and coupled to the motion of the mantle. And another application of this is to study the length of day variations of the Earth. You know that the Earth is slowing down because it's losing energy, but also on top of that secular slowing down of the Earth, of the rotation, there are some variations of the rotation rate. It's actually just milliseconds over a few years, but you can measure them thanks again to the radio telescopes and the quasars. And most of that signal that you see in the length of day variations, I should have put a plot of that. But it can be explained by the loading of the ice masses or displacement of the ice masses, basically hydrological loading, and also the loading of the atmosphere, because the atmosphere also exerts torques on the Earth. But of course, the question is, what about the core? The core can also exert torques, as we have seen. And so what we want to find out now is how can these modes of the flow, these inertial modes, if they can exert torques on the mantle in the time scales that appear in the length of day variations. So this is actually what I'm doing at this moment. For that, to accomplish that task, we started first trying to implement a stratified layer at the bottom, at the top of the core, as you see here. So this is the interface between the fluid core and the mantle. And we wanted to put a region at the top of the core that is stratified in density. And then the other part will be just simply like well mixed with no density stratification. So we started doing that. We included that part in the code. And that is also a work in progress. This is, Fleur is not here. She didn't come. She's one of the students that also works at the observatory, and she's doing part of this with us in our group. Another application of the code that we have written is to study the onset of thermal Rossby waves. So these are a little bit different from the Rossby waves that we studied at the beginning. But basically, if you have your inner core of your planet and the outer core at a different temperature, and if that the temperature difference is large enough, then you can get an inertial mode self-excited. That means that is what we call in fluid dynamics is unstable. And this is very important for the people that study the geodynamo, because they need to go to have a dynamo going in the models of the geodynamo. To have it going, you need to be in the regime where the thermal Rossby modes are excited automatically. And so we have the code kind of tested with we tested the thermal equation and we reproduce all the previous results. And this is another application of the code. Now, this is something that I really wanted to show here in particular because, I started playing with the stratification part because we can make a model of a star. It's a very simple model, but this in particular is kind of like a Gamma Doradus star. You can think of it the simplest version of an intermediate mass star, where the core is convective and is surrounded by a stratified envelope, just like the opposite as in the sun. So I went ahead and I started computing the eigenmodes of such a system. So for that, we used the code. We computed what I'm showing you here. Each dot is an eigenmode, and I'm changing the Brunt-Väisälä frequency, which is the maximum frequency that the internal gravity modes can have. And I'm just changing the Brunt-Väisälä frequency corresponding to the stratified region. And then this is the result. The color represents simply the damping. So the bluer and the larger the dots, these are the least damped modes, which means that they are the easiest to excite. And you see, there's a lot of modes. Some are very easily excited, but not unstable yet. They still have like a negative decay factor. But these are internal, G modes. And you can see them more clearly here. This is the frequency, the frequency compared to the rotation, of course, to make it dimensionless. And these are some tracks that show the family of G modes. And these blue ones, for example, these ones here, These are the dipole modes, the L equals 1 dipole modes. And you can see a little bit with more difficulty, there are other tracks, the green tracks here. Those are what I believe, I haven't really looked, but they could be the L equals 2 modes, G modes. But now there is something strange here. There are these very kind of horizontal lines that, well, horizontal means that they don't depend on the Brunt-Väisälä frequency. So when I saw this, I thought, oh, maybe those are some sort of inertial modes. And I'm going to focus on this plot. This plot is basically these two combined into one, but with a different, instead of coloring with the Brunt-Väisälä frequency. And you see that this region corresponds to this kind of kink in the plots. So this is the zoom in of that region that I showed you before. So you have these nice dipole G modes, and you can already see in the background those horizontal lines, which I suspected, oh, those are inertial modes. But there is a funny situation here. There is kind of it's kind of like an avoided crossing, like the ones that we saw before. So let's see. I made a plot of one mode just there, and it turns out to be this. So this is the convective region, and you see there is an Eigen mode there. It's an inertial mode, and in the radiative, the stratified envelope, you see a very nice G mode. You can even, well, if you have good eyes, you can count the radial order of such a G mode. So I was very happy that I could see this. And you see that the amplitude of the mode is, well, it has good amplitude both in the radiative, or the stratified part, or also in the convective part. Now what happens in other regions? For example, this one, this region over there. So I'm plotting here the least damp. This is the blue, the dark blue one here, and it happens to be this one. You see that the amplitude is in the convective region is very small. But if you plot one of the background modes, the one that is very, has a different color here, it happens to be just this. It's an inertial mode that only exists in the core. So it's a completely different situation, you see, because they have very different dampings, although the frequency is exactly the same, well, very much the same, they do not couple because they have different dampings, something that we already saw before. So this is probably the whole story that I wanted to convey, that there is this avoided crossings happening, and they are very important, but they haven't really been appreciated much in the literature, but it's something that probably in the asteroseismology group of researchers is better appreciated. But still, there are many things that are very much a mystery. I'm going to say now a few words about other instances where inertial modes appear, and this is one of the probably most exciting ones in the recent years. This was the detection of Crosby modes in the sun. I think this was in 2017 or 2018. It's fairly recent, and they found by looking at. Well, actually, I'm not very familiar with the observational technique, but they managed to observe the frequency of the mode and the azimuthal order of the mode, and they plotted this. And when you go and compare with the theoretical dispersion relation of the Crosby modes, which is this, then which is plotted here, you see like an excellent match. So these are Rossby modes in the sun. And so this was 2017. Now this is last week. Last week, there was yet another detection. This appeared in Nature. This is the old, well, the one that I showed you before, just before. These are the Rossby modes. And there are this other region that shows some power that they think, well, the authors claim that they are actually Rossby modes. Although, in my view, that cannot be for a number of reasons. But well, they call them HFR modes, like high frequency Rossby modes. But basically, if you read this paper, which I hope you do, is they basically say that they have no clue what these are. But they still claim that these are Rossby modes, although in my view, these are not really Rossby modes, and I cannot really wait to actually run my code and see if I can reproduce this branch, which I don't think. Well, you'll hear about it if it's actually true what I say or not. Okay. Now, there is another one, another example. Are we okay? On to 3. And what is the time now? 3. Oh, okay. Well, okay, if nobody kicks us out, it's okay. Well, I have, this is probably the last example. Resonance locking. This is a situation where in the inertial or G modes resonating in a planet or a star can determine the migration rate of the satellites. So, for example, in the Jupiter system, the oscillations in the planet can actually determine the migration rate of the satellites. You know, the satellites are actually going, you know, the orbit is increasing because they are losing energy because of dissipation, and that dissipation is in the planet itself. And if you see here, I'm plotting here what is called the characteristic time scale of the migration of the satellites. If you happen to be in this region when the frequency of the satellite is just slightly above the frequency of a mode in the planet, in the central planet, then if the orbit of the satellite was perturbed a little bit further in, then you will get further into the resonance. They will decrease the characteristic time scale of the migration, which means that the planet will be forced then to migrate out yet more. So it will kind of keep it in place. But if you were to perturb the orbit so that the satellite is a little bit lower in frequency, then if the frequency of the mode in the planet is changing because the planet is evolving or for some other reason, then it will catch up with the frequency of the satellite. So in the end, what is going to happen is that the satellite will be forced to migrate at the rate that the damping of the mode in the planet determines. And this is a fairly recent idea that is only being applied. For example, this paper from, I think it's from a few weeks ago, that determines applied to Io and Jupiter, and this one is probably a little bit older, but in the Saturn system, and well, this one is a resonance with a G mode, and this is a resonance with an inertial mode, and Well, I think I'm going to skip a few things that I wanted to say more, and I will leave it to the summary. And yes, so thank you so much.
Okay, so we have time for a few questions. Anyone?
Yeah, thanks for a very nice talk. What I didn't quite get when you were talking about the free coordination of the Earth, as I understand it, that's related to the misalignment of the different rotation axes?
Yes,
So
exactly. Yeah.
how does that frequency actually change if you increase that misalignment?
That's a good question. The frequency is very close to the frequency of the rotation. In fact, imagine that you had a you had a planet that had completely inviscid, perfect fluid inside. So the fluid is actually decoupled because there is no way to move it. It's like when you have your cup of coffee, right? And you have a crumb kind of in the way. And then you say, oh, I'm going to spin it to drink my coffee, but you do that and the crumb stays in place. So the same thing, it's very hard to couple if the fluid is inviscid. So in that situation, if the planet is spinning and the fluid is like spinning in another direction, your frequency, the frequency will be exactly 1. But since it's actually moving along a little bit, so the frequency is not exactly 1, but close to 1. So it's actually very hard to visualize. Although the concept is very simple, it's simply a misalignment, but is the math that goes into figuring out the exact frequency is quite complex. And it's complex.
Thanks, Santiago. So we see lots of inertial mode coupling with gravity modes in stars, but is there an exact or an approximate formula that can tell us how the inner core spherically couples to a mode, an envelope mode of a flattened star? Is that, do you have that, or is it too complicated?
Well, I can model it. Well, for a flattened star, if it's very flattened, I cannot do it. But if the flattening is moderate, the code can do it. And I think, well, there is some sort of an analytical approach that I saw in a paper from Rita Maria Oasani. Actually quite recent. It's the paper that I was reading from the beginning of the I think it's from 2020. That she actually, this is actually the paper that inspired me to do this study, because she tries to do like figuring out a coupling constant between the inertial mode and the G mode, and to see which ones have more chance to be coupled. But one thing that is not clear to me is how the viscosity or other diffusion effects determine this. Because as I shown, the diffusion or the damping, for whatever reason, viscous, thermal, magnetic, can influence the avoided crossing. So and the coupling is basically that, right? That is when you have a G mode and an inertial mode crossing, so they coupled, and the coupling will be actually determined by the damping also. So I think there is, it's not very clear to me what, it's probably something worth looking at.
Okay, any other questions?
Hi, thanks for the talk. I had perhaps a bit of a naive question on the simulations that you showed, where you showed the inertial modes and the gravity, the frequencies for the gravity waves for Gamma Doradus stars, for example.
Let's see.
So I was just wondering, so you have a convective core and then a stratified envelope. How exactly would your frequencies change based on the chemical composition of your core? So if it was a hydrogen core or a helium core, how exactly would these frequencies change?
Since this is a very simple, I'm assuming that everything is homogeneous, like an homogeneous composition. So, but I can do, I can set a chemical composition gradient, which will give place to yet another kind of stratification. So it will be actually very much like the density stratification, like a stratification in density, but this will be in the chemical, it will be kind of like a chemical gradient. And actually, if you look at the equation is actually identical. It only has, the parameters are different. And this is also included in the code. But at this stage, I cannot put a real model of a star like the one produced by MESA, for example. I cannot do that yet. Someday, maybe one of you will manage to do it.
Okay, I think we have to end here. So let's thank Santiago again. And if you want to speak to him, I think he will be in the coffee room for a bit. So
excellent.
Okay, thank you very much.
Thank you.
You have the slide. No, you have the slides or something here.